This question is about enthalpy changes for calcium chloride and magnesium chloride. State the meaning of the term enthalpy change. So enthalpy change is defined as heat energy change. We need to be specific that heat energy change occurs at a constant pressure. Figure 1 shows an incomplete Born-Haber cycle for the formation of calcium chloride. Complete Figure 1 by writing the formulas, including state symbols, of the appropriate species on each of the 3 blank lines. So the Born-Haber cycle for calcium chloride links the formation from the elements to the lattice formation from the ions. So we've got the calcium chloride solid at the bottom. We would need the elements for calcium chloride, which are calcium and chlorine. Remembering that chlorine is a diatomic gas and calcium is a metal. So we can see that in terms of numbers, there's 1 calcium, 1 calcium, 2 chlorines, 2 chlorines. So we don't need to do any further balancing. We don't need to put any numbers in front of any of the species. We're linking the elements on the left to the gaseous ions that do lattice formation. So lattice formation is from the gaseous ions, calcium ions and chloride ions. We need 2 chloride ions in calcium chloride, both with a gas state symbol. Make sure the difference between your G's and your S's is clear for the examiner. If it is unclear, the tendency will be to mark it wrong. If they cannot determine whether it's an S or a G, then they will not be giving you the benefit of the doubt. They will be looking for clarity in those state symbols. So the first thing that happens after we've done our enthalpy of formation is that we are going to do some atomization of the calcium atoms. And then we're going to, we can see that the calciums become calcium 1+, so that would be first ionization energy of calcium. We would then need to ionize the calcium again to make it 2+, so there would now be 2 electrons. We still haven't done anything to the chlorine. At this point you could have done the atomization of the chlorine if you wished. So we've put all the species on the lines. If we were to continue labeling the changes, here we've done the second ionization energy of calcium, and here we've done the atomization of chlorine. And then on this side we would have 2 times the electron affinity because we've got 2 chlorines. This would be 2 times the atomization as well. And then here we've got, because the arrow's pointing up, it's lattice dissociation, breaking the lattice, not formation of calcium chloride. Table 1 shows some enthalpy data. Use Figure 1 and the data in Table 1 to calculate a value for lattice enthalpy of dissociation of calcium chloride. So what we're going to do is we're going to put those values onto that cycle so that we can visually see the numbers on the cycle. So if we go back here, and we're just going to change the colour of the pen so it's a bit clearer. So we had the formation here, -795, and it's a down arrow, so it makes sense. Then we atomized it, 193. Now we've got to do first ionization energy, 590, and second, 1150. And then we want 2 times, because we're making 2 chlorine atoms, so 2 times the atomization of chlorine, and 2 times the electron affinity. And again, it's a down arrow, so it's minus. And we're trying to find X, this arrow here. Now you can use different methods. If you've learnt the method that formation is all the others added up together, you need to be careful on this one because this is dissociation. So it would be all the others minus the dissociation value. I'm going to use the Hess's law rule, which tells me that X arrow starts here and ends here. So if I start at this level and end at the same place, but going a different route, I should get the same answer. So when I go upwards, I'm going to have a positive number. When I come downwards, I'm going to have a negative number. So I'm going to say that X equals, so I start at the bottom, 795 becomes positive because I'm going up, and then 193, and then 590, and 1150, and then 2 times 121, and then I'm going to add on the 2 lots of minus 364. So I'm following that arrow, but it's downwards. And then I'm going to be back at the end of my Hess cycle diagram. So I would type all of that into my calculator. And if I put all of that into my calculator, then I should get the answer 2,242. Will be positive because the arrow points up, and it's in kilojoules per mole because I've added numbers in kilojoules per mole. Magnesium chloride dissolves in water. Give an equation including state symbols to represent the process when the enthalpy of solution of magnesium chloride is measured. So that's when the solid dissolves in water. So you don't add water as a reagent. You could write AQ if you liked. I'm not going to bother. But you become the aqueous ions. You dissolve and you become the aqueous ions. Table 2 shows some more enthalpy data. We've got lattice dissociation of magnesium chloride and their 2 hydration enthalpies. It says calculate the enthalpy of solution of magnesium chloride. So I'm just going to rewrite that equation. You may have learnt a formula for this and you may want to use a formula. I prefer to use Hess's law because it's going back to first principles, helps me understand how to do things. So I've got lattice dissociation. So if this lattice dissociates into the gaseous ions, that arrow there is 2493. We're trying to calculate the top arrow, the enthalpy of solution. And this side, if we're going from gaseous ions to aqueous ions, we've got 1 of the magnesium and 2 of the chloride ions. So if I want to find x is we're going to go from the start of the arrow to the end of the arrow, but a different way. So we're going to have our 2493, and then we're going to add minus 1920, and we're going to add 2 lots of minus 364. I'm going to type that into our calculator and we get minus 155. Then it says the enthalpy of hydration of calcium 2 plus is minus 1650. Suggests why this value is less. Exothermic just means less negative, so we just really want to think why this number is less than minus 1920. So what's the difference between Mg2 plus and Ca2 plus? So they're both group 2, so they both have the same charge, but calcium ions are bigger, more shells, so have lower, because they've got the same charge but they're bigger size, so lower charge density. And if they're if their charge density is lower, they will have weaker attractions to the opposite, we're doing hydration here, so to water. And it will be, let's add to that just for completeness, since they're positive ions, to the delta minus oxygen in water. If this question had asked us to compare like lattice enthalpies, we would have a similar answer, but it would be weaker attractions to the oppositely charged ion.